All right, we're going to take a look at 2015 question number 2. Okay, and it says that f and g be the functions defined by f and g, and that r and s be the two regions enclosed by the graphs of f and g shown in the figure above. So what I've done to start with is I've taken the two equations that were given here, f and g, and put them in my calculator. So f is y1 and g is y2. So on my paper, I'm going to denote f as y1 and g as y2, just so that I have them, okay? So I know, like, for future reference, which ones they are. The other thing I've done on my calculator is I've gone ahead and set my window to match what's on my graph. So notice how the x-coordinates go from 0 out to 2, okay? And then notice how the y-coordinate goes from 0 and then to 4, okay? So I've set my window to be the same thing, so on my graph in calculator, I can see the same thing that's on my paper. And if you notice, y2, or g, is the curve that kind of goes up and then down the hill and then the valley. So we'll go ahead and label this one g. I'm going to label it in the two different spots. And then f, or y1, is the blue function, the curve that just kind of swoops. Okay, so we're going to call this f. Okay? Okay, so I've marked those on my paper as well. Okay? All right, so in part A, find the sum of the areas of region R and S. So to find the area between two curves, what we're going to do is we're going to take the area of, or the integral of the top minus the bottom. Okay? So for part A, we're going to go the integral from A to B of top minus bottom. Okay, so if we notice that on this integral, the area of the regions R and S, it changes, right? So on this first region, we have a top function of g, but in region S, it changes and our top function is now S. So what we need to do is we need to figure out this point of intersection, okay? So on my calculator, I'm going to go second trace, intersect, and the first curve needs to be on y1, so I press enter. Second curve needs to be on y2, so I press enter. And then for the guess, I'm already pretty close, so I can just go ahead and press enter. So the x-coordinate is 1.033. So on my paper, I'm going to put let a equal, and this isn't the same a that's here, right? This is a different a. That's just kind of a, oh, let me change screens here. The a here is not the same as the a here. I'm using this a as a point of intersection, so I'll make it capital A. Let capital A be 1.0328319. That's the x-coordinate of the intersection. And then I'll go ahead and say let B equal 2.4011081, just in case I need either of these 2 points. Now what I can do is, because I've defined capital A to equal that, anywhere where I need that number, I can just put A. Okay? So the area for region R is just going to be top minus bottom, right? So if I drew in this slice, the top function is G, the bottom function is F. So if I take the integral from 0 to A of the top function, G, and subtract the bottom function, F, then that would be the area of R. And then I'm going to add on the area of S, right? So in this case, the area is the top minus the bottom, which should kind of sort of make sense if we think about this, right? The area of F would be all of this, right? And then the area of G would be all of this. And I want the area in between them. So if I take the area of F minus the area of G, I would be left with the difference, which would be region S. Okay, so hopefully that kind of sort of makes sense. If it doesn't, don't fret. So top minus bottom, F minus G. The x-coordinate here would be all the way out to 2, so from A to 2. And top is F minus G. Okay, And remember, we saved f as y1 and g as y2. So we're just going to go ahead and type this in the calculator. If you go to math 9, that's your integral. We're going from 0. Well, wait, hold on a second. Let me store that point of intersection as a. Okay, there we go. So now that it's stored as a, I can just type in a, so now it matches what's on my paper. So math 9, 0 to a, and we had g, which was y2, minus f, which was y1, dx, plus, now the other integral from a to 2 of y1, which is f, minus y2, which was g, and then press enter. And we should get 2.004. Okay? No units are necessary on this one because it didn't give us any units to start with, so we can just leave it as 2.004. Okay, part B, region S is the base of a solid whose cross sections perpendicular to the x-axis are squares. Find the volume of the solid. And we've kind of talked about this a little bit before, but if I'm taking region S and I want the area of the cross sections, actually, you know what? I kind of want to leave that on there, don't I? Let's just get rid of some of this stuff. Okay, so I'm just concerned with region S now, and it wants the volume of the cross sections. So if I took out, think of region S as like a loaf of bread, okay? So we're going to take that loaf of bread and we're going to pull out just this one slice here. Okay, so if I take out this slice, that's going to form a square. It's not a very good square, but it's a square. Okay? So no matter what, this side, this slice, this bottom part of the slice, is that segment there. So that's going to be f minus g, okay? And if it's a square, then both sides are f minus g. So to calculate the integral, what we're going to do, or what we're going to do to calculate this, is to set up an integral of the areas of each of my cross sections. Okay, so the area here was a square, so f minus g squared is the area of one slice, and we're going to go from A to 2. Let's change this to just say area. So the area of each cross section, the area of this slice is f minus g squared. Okay, and this is all comprised of all these different squares, right? And I know it's hard to visualize, but just kind of bear with me. So to find the volume, we take the integral and add up all these slices from a to 2 of f of x minus g of x, and we're going to square that. Okay? All right, calculator problem, so we're going to go ahead and type it in. Math 9 a to 2, and then in parentheses y1 minus y2, whoops, alpha trace y2, and then we're going to square it, and then it's dx. Okay, 1.283. That's it for that one. Okay. For part C, let h be the vertical distance between the graphs of f and g in region S. So let's erase some of this scratch work from before. Okay. The area, or h, is the vertical distance between the graphs of f and g. So that segment there represents h. So h equals f of x minus g of x. Okay. And I want to know, find the rate at which h changes with respect to x when x is 1.8. So I want to know what is the rate of change of this with respect to x. Whoops. What is the rate of change of that with respect to x at x equals 1.8? So if I want to know a rate of change then that is a derivative. And I'm going to take the derivative of this. And this one's just pretty easy because it's just a straight derivative. So the derivative of f is f prime. The derivative of g is g prime. And if I want to know specifically at 1.8, I'm just going to plug in 1.8. So h prime of 1.8 equals f prime of 1.8 minus g prime of 1.8. Okay? So on our calculators, we're going to go math 8. That's how you get to the derivative. D over dx of y1 evaluated at 1.8 minus the derivative again, d over dx of g, so y2 at 1.8. Okay? Answer is negative 3.812. Okay? And that's all we got to do for that one. Okay? So let's talk about the points. For this one, you would have 4 points. 1 point for your limits, your bounds, so from 0 to a and from a to 2. 2 points for the integrals, all or nothing here. And then 1 point for your answer. Whoops. So again, 1 point for the limits, 2 points for the integrals, all or nothing, and then 1 point for the answer. On part B, you would get 2 points for the integral, all or nothing, and then 1 point for your answer. And then on part C, you would get 2 points, 1 point for considering h prime, and then 1 point for getting your final answer. Okay? All right, let me know if you have any questions.